Hello, my name is Patricia Suzanne Eastwood, and today we will be discussing Lab 3, the magnetic field of permanent dipole magnets. So the first thing we want to discuss are the goals of the lab. So first we wanted to measure a bar magnet's magnetic field. Then using this data, we wanted to determine the distance dependence of the magnetic field. Finally, we wanted to compare these values to magnetic fields derived from the Biot-Savart law. So the materials that we used for this experiment included a bar magnet, a smartphone, in this case an iPhone 6S, the Sensor Kinetics app, a ruler, a meter stick, tape, and the Excel document we were given. So we wanted to make a few assumptions. We assumed that the magnetometer app defined the x-axis as pointing along the width of one's phone, the y-axis is pointing along the height of one's phone, and the magnetometer app defining the z-axis as pointing out of the screen. So as our procedure, we first downloaded the sensor app onto the iPhone. We then calibrated and determined the exact location of the sensor within the phone. So this was so that the Earth's magnetic field would not impact our results in the net magnetic field. Therefore, we wanted to zero out the Earth's magnetic field by determining the zero component for the x, both orthogonal and along the axis of the magnet. So then finally we measured the distance to obtain a magnetic field of 1,000 microteslas for the x component. Using this distance, we then measured the magnetic fields at distances proportional to the original measurement. So first I want to talk a little bit about bar magnets before we go through the results and the data. So we know that the field direction is outward from the North Pole and into the South Pole end of the magnet by convention. We also know that the magnetic field is going to be strongest within the magnet, and the greater the distance, the smaller the magnetic field experienced. So, kind of the principles explained, our goal in this experiment was to be able to determine N. So we want to determine the power of the distance. So we know that N is going to be a negative number, but the question is, what is this number going to be? And I want to describe these variables. So K is a series of constants, so the example is a magnetic moment, and then times distance to the power of N equals the magnetic field. So again, we know that the further away the distance, magnetic field is going to decrease dramatically. The question is to what power? So because we want to be able to graph this to determine N, we know that this will be very difficult to graph B and R just because it would be curved and it would be very hard to measure this. So therefore, if we take the logarithmic values of the magnetic field and the constant and distance, we're then able to calculate N as the slope of this graph. So here's my data in Excel. I was able to be able to plug some of these values in. We saw that the magnetic field decreased dramatically at these distances that were proportional to the original distance measured, and we were able to find that the slope was about -3. Therefore, since N is the slope in this case, we know that N is going to be -3. So we know that distance is going to be cubed inversely, well, the distance cubed is going to be inversely proportional to the magnetic field. And that was what we were able to reason from our results and from this data. So the first question is, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would these results have changed? Well, this would have been a less accurate result due to the inability to account for the Earth's magnetic field, which would affect the net magnetic field. So our results would be less accurate, and we would definitely not want to be able to do that. And then the second question is, what if you stuck two identical magnets together end to end and run the experiment again? How would these results differ? So we know that the magnetic fields of the magnets would be added together, thereby making it stronger. It wouldn't necessarily make it double just because of the distances between the magnets. So the goals of our code, we actually wanted to create a code that mimicked our observation results, and we wanted to make sure that these results were aligned. So we calculated the magnetic field through this formula here. we wanted to alter the magnetic moment accordingly and calculate the magnetic field produced by a dipole, so as in the prior example. So then we wanted to visualize the fields along the axis perpendicular to and along a 45-degree angle in relation to the bar magnet, and then we wanted to adjust the scale of the field arrows and their distances accordingly. So ultimately, the goal of this was to actually find mu and see how these results aligned with our original data. So here I kind of want to go over my code briefly. I did get very similar results, and I calculated both along the axis perpendicular to and the 45-degree angle. I did adjust the B scale and mu to be 13. So then finally, I was able to conclude that my observed results for the 45-degree angle did align with the calculated results from the code, so therefore the results were fairly accurate to one another, and the magnetic field is inversely proportional to the distance cubed, as said previously. I hope you enjoyed my presentation.